Are there truly different sizes of mathematical infinity? Imagine standing at the edge of a vast ocean of numbers, wondering if all infinities are the same size or if some are bigger than others. That question has puzzled mathematicians for centuries. It turns out, in the world of mathematics, there are indeed different sizes of infinity. This idea is part of set theory, a branch of mathematics that studies collections of objects called sets. Let's start with the simplest infinite set, the natural numbers. These are the numbers we count with, 1, 2, 3, and so on. Since they go on forever, we call this a countable infinity. A set is countably infinite if you can list all its elements in a sequence, matching each one with a natural number. For example, the even numbers 2, 6, 8, and so forth are also countably infinite because you can pair each one with a natural number. This shows that, even if a set seems larger, it can still have the same size of infinity as the natural numbers. But then, there are infinite sets that are uncountably infinite. These are bigger than the set of natural numbers. A famous example is the set of all real numbers between 0 and 1. This set includes every decimal number between 0 and 1, like 0.3, 4, 5, 6, and so on. Mathematician Georg Cantor proved that you cannot list all these numbers in a sequence that pairs each with a natural number. No matter how hard you try, some numbers will always be left out. This means the infinity of real numbers is a larger kind of infinity than the infinity of natural numbers. This discovery leads to a hierarchy of infinities. The smallest is the countable infinity, called aleph-null, written as letter 21350. The next size up is the continuum, which is the size of the real numbers, often written as 2 to the power of letter 21350. Some mathematicians wondered if there was an infinity size between these two, but it turns out that within the standard rules of set theory, this question cannot be answered definitively. It remains one of the biggest mysteries in mathematics. Further research has shown that different infinite sizes can have surprising relationships. Some infinities are equivalent in size, even if they seem very different. This ongoing work reveals that infinity is not just one thing but a whole spectrum of sizes. These ideas challenge our intuition because they show that infinite sets can behave in ways that are very different from finite sets. They also have practical implications in areas like computer science and analysis, where understanding the size and structure of infinite sets is important. In summary, mathematical infinity is not a single concept but a range of sizes. The smallest is the infinity of natural numbers, and larger infinities, like the set of real numbers, exist beyond it. This discovery opens up a world where infinity is more complex and fascinating than we might have imagined, inviting us to think about the endless possibilities hidden within numbers.